Okay, assalamu alaikum. Okay, we were doing asymptotic condition, yeah, and this asymptotic condition which says that the actual orbit, which is which is psi, in fact tends to the asymptotic orbit as t tends to minus infinity or plus infinity. Yeah. So this was the condition. This was the condition which we would like to which we were studying in our last class. That is the actual orbit, which is the orbit at t is equals to 0. It tends to the asymptotic orbit psi in or psi out as t is tending towards minus infinity or t is tending towards plus infinity. That was our point in the last class. Now we restrict ourselves to the psi in vector, and let's say we restrict ourselves to the psi in vector and let's take a Gaussian function. A typical Gaussian function or the wave function for psi in is some traveling wave, and this Gaussian function has a width which is a and has in fact width which is xi and is centered around a point which is denoted by a. So let's say we 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 will restrict uh, to the to the asymptotic uh, vector psi in, yeah, psi in as a Gaussian function, as a Gaussian function. So the wave function for psi in are always Gaussian. And so in position space, this is proportional to e to the power minus x minus a whole square divided by 2 xi square, where a is the center of the Gaussian function, and xi is the width, i.e. we could write it as, so, so we could think about, so this is a, the center, and this is in fact the width, which is xi. Yeah. So this is the Gaussian function. So we know that a free particle, obviously, when we talk about a free particle, it's a plane wave, and it evolves as a Gaussian function. So that's why we talk about because psi in is a asymptotic function. That is, it is a function which is it is a particle which is free. Then so we need to express our psi in using a Gaussian function. So the wave function for freely evolving Gaussian function, that is the probability density for such a wave function, can be then can also be determined. Uh, so we know that a free particle evolves as a Gaussian function. Yeah, the wave function, the wave function for a freely evolving Gaussian function, that is the probability density density is is given by. So we can write the probability density x u naught of s. So this is the asymptotic wave function psi square, which is equals to 1 plus s square upon m square xi to the power 4 whole divided by 3 by 2 exp, the exponential function, because it is associated with the freely evolving function, minus x minus a whole square divided by xi square plus s square upon m square into xi square. This is the function. Yeah. And so S is some factor which basically describes the evolution in time, and that is the Gaussian spread out by a width S in this time. Yeah, where you can say where S is a factor describing evolution in time. In time, i.e. क्या मतलब है इसका? That is the Gaussian function. Gaussian function spreads out by a width S in time. So in this case, one would say that we have this. In our case, we would have this V, that is, which is H minus H naught. If you remember from last time, U of S psi in whole square, and this is equals to integral d3 x V of x square. Then we have 1 plus s square upon m square xi square by 3 by 2, and the exponential function, which is minus x minus a whole square upon xi square plus s square plus m square xi square, this quantity. Yeah. And so if we talk about the uh, the sufficient condition and applying the condition 0 to 3, then this quantity V u naught of s psi n is less than or equals to, where V of x is 0 to 3, those conditions, then this is integral d3x V of x whole square to the power half. So uh, this cancels out, so we take a square root times the integral minus infinity to 0 ds of 1 plus s square upon m square xi square की power 3 by 4. Yeah, with a minus sign. Yeah, so this is minus, this is with the minus sign. Okay, so and this is in fact, the exponential function goes to the denominator because the exponential function is e to the power minus x minus a whole square upon that quantity. So if you say e to the power, that would be 1 upon e to the power x minus a upon some quantity which is in the denominator. So for a long interval of time, then that e to the power some quantity would be a very small value, and so we can neglect it, and this is in fact less than infinity. So it is this quantity which is basically under these integral and the power half. It is definite, that is, it is not infinite, but it is definite, or it is finite, and which is less than infinity. So Gaussian functions are um, uh, in fact, Gaussian functions basically provide overall complete basis to the scattering phenomena. So one could say that Gaussian functions are an over complete basis, and that complete basis is represented by the projection operator. So in some equation above, we have that 2 second term, and this is equals to 1 upon pi time integrals d2, some, in fact, some basis, sum over all the bases, and the projection operator, which is basically this operator. So we call this as a projection operator. Yeah. So this is just an example. So this is done for every state sign, and this every state sign is a linear combinations of the Gaussian function. Then we can apply the argument which is given above. That is the argument which says that in fact u dagger of t, u naught of t psi in has a limit. So what we need to define here is defining a limit. So we say that, so this is so this is done. Uh, every state psi in is a linear combination, is a linear combination combination of Gaussians, or the Gaussian functions. Then one could apply the argument. What was the argument? That u dagger of t, u naught of t psi in was the argument, has a limit. This was the argument. Then apply the argument, this argument, after triangular inequality to each quotient. And the linear combination gives the limit. Yeah, so it is not just for one, in fact, psi, but all those particles interacting with the target, that applies for all those particles, that this argument would apply some limiting value. Yeah. And so this is basically this in fact describes the Gaussian function. In fact, this completes the proof of the asymptotic condition for any Gaussian wave function of a width, let's say of width a, and of a width s, or whatever जो हमने ऊपर लिया है, and hence for any linear combination of Gaussian functions. So not just for one particular particle or free particle represented by psi in, but for all particles interacting with the target. So we say this completes the proof of asymptotic condition for any Gaussian wave function of a width which is given by some factor xi, and hence for any uh, linear combination of such Gaussians. Yeah, so this is basically uh, the asymptotic condition. Now, next we talk about, because we want to measure the scattering, yeah, or the scattering amplitude. So we define a quantity which is known as the molar operators, molar operators. So what is basically Muller operators? They are basically derived from this limiting condition. So now the asymptotic condition, basically it guarantees that psi in some Hilbert space is in fact the in asymptote of some actual orbit, and similarly psi out in some Hilbert space is the out asymptote of some actual orbit. This is in fact guaranteed by the asymptotic condition. So what asymptotic condition guarantees, it says that the psi in and psi out are the limiting values of the actual orbit. So what asymptotic condition applies? Asymptotic condition guarantees that any psi in, or for that matter psi out, in any for any psi in Hilbert space is in fact the in asymptote in asymptote of some actual orbit, of some actual orbit. Actual orbit means u of t psi. And similarly, you can say the same thing for the psi out as well. Additionally, it also says that from the proof it is clear that the actual state, that is the actual orbit psi of the system at time t is equals to 0, is in fact linearly related to in asymptote, or it is linearly related to the out asymptote. Yeah. So in addition, or rather additionally, the asymptotic condition says that the actual orbit, or the actual state, actual state, in fact psi, is psi of the system of the system at time t is equals to 0, of the system, that is the incoming particle and the target at time t is equals to 0. So this is t is equals to 0. This is t is equals to at time t is equals to 0 is linearly related to the to the in asymptote psi n. And what is that linear relationship? So if you remember, we have psi, and this psi is equals to limit t is tending towards minus infinity. So this is t is equals to minus infinity. So t is equals to minus infinity. Ut, u dagger of t, and u naught of t psi n. This is that linear relationship. So it means that we can say that this psi is equals to, uh, let us इसको इस तरह से लिखें. So let us denote this uh, limit t tends to minus infinity, u dagger of t, u naught of t, uh, by by a symbol, by a mathematical objects omega plus. So then psi, the actual orbit or the actual state, is linearly related to the in state with the help of this mathematical object. And this mathematical object is in fact the Muller operator. We will call it as a Muller operator. Uh, similarly, the actual state, the actual state psi at t is equals to 0 will evolve into. So then now we talk about psi out will evolve into an out asymptote, out asymptote psi psi out in a linear fashion, in a linear in a linear manner. And what is that manner? Psi this equals to limit t tends to plus infinity, u dagger of t, u naught of t psi out, and this is equals to omega minus psi out. So, so we have these two linear relationships. Yeah. So it means that we now have two operators, two mathematical operators, omega plus and omega minus, defined in the limits of t tending towards minus infinity and t tending towards plus infinity. So the two operators uh, omega plus minus, defined as the limits And what is that limit? So we define omega plus minus is equals to limit t tending towards minus plus infinity u dagger of t u naught of t are the molar molar wave operators. So they are called as, or rather are called as molar wave operators. Yeah. So what are they? They are limits of unitary operators. They are therefore isometric. Isometric means that is they are distance preserving transformations. Yeah. So what are these operators? They are limits of the unitary operator. Therefore are isometric. Metric, that is an operator. An isometry. Isometry is the distance preserving transformation. Yeah, so this is basically it. And now this operator acting on any vector in the Hilbert space, they give the actual state at t is equals to 0 or vice versa because we are talking about the isometry. Yeah. So uh, what does it do? So acting on any vector or state in the Hilbert space, they what they do, they give the actual state at t is equals to 0. That would would evolve from basically आएगी or evolve into, that is goes to, or evolve into the asymptotes represented represented by by vectors, basically psi in and psi out. So one could think about this pictorially. So this is some asymptote, and this is the actual orbit. This is the actual orbit, and it basically evolves into the actual orbit. So this is the in asymptote. In asymptote, that is you you u naught of t psi in, and it evolves into psi due to this operator, which is the molar operator, acting on psi in. Yeah. And in fact, this is your actual orbit. So this is the actual orbit. which is in fact u of t into psi. Yeah. And then we could also talk about, in fact, the out asymptote, and this is in fact evolve into. So this is the this is the this is the this is the asymptote, which we call it as out asymptote. Yeah, that is u naught of t psi out, and this is in fact the actual orbit, which is u of t of psi, and this basically something like this. So we have this psi, which is minus psi out. Yeah. So evolve into or evolve from. So evolve, we have this this basically psi, the actual orbit, is evolved from the in asymptote, and this psi, the actual orbit, this evolves into the out asymptote with the help of this omega minus. So in some sort of an accelerator or collider, acceleration and the collimation, they are produced by devices. Yeah. So they are they those devices are large magnets or coiled magnets, which basically or some mechanism which accelerate the particles. So these acceleration and collimation, they are produced by some devices, um, they are produced in some definite incoming wave packet. Yeah. So the psi in can be represented by some incoming wave packet, and similarly psi out can be represented as some outgoing definite wave packet. So uh, in actual practice or in colliders or accelerators, acceleration, and collimation. So acceleration is done by electric field and collimation is done by the magnetic field. आपको पता है produce uh, produced produced by devices produces some definite incoming wave packet. Incoming wave packet, and is sort of denoted by, let's say, उसको psi in को अब हम let's say नाम दे दें phi, which is the incoming wave packet, and similarly the measuring devices or the detection devices, measuring devices are arranged such that a definite out asymptote is produced. I, let's say उसका नाम हम दे दें psi out, and psi out is chi. Yeah, so we have a definite incoming packet and a definite outgoing packet, and the definite incoming wave packet is denoted by phi, and the definite outgoing packet is denoted by chi. Yeah, so the definite incoming wave packet is basically due to all those devices which are responsible for acceleration and collimation. That is, all those devices which produces electric field, and all those devices which produces magnetic field. And the outgoing wave packet is in fact a measure of the scattering, which is measured by some sensor or detector. So in fact हम जो limiting cases हैं, we would give them a notation. And what is that notation? So uh, we use the following notations. Notations: I uh, omega plus psi, sorry, mm, omega plus phi, because साइन जो है वो phi के बराबर है, एंड दिस इज, इसको हम phi प्लस से जाहिर करेंगे. ये नोटेशंस हैं. एंड सिमिलरली ओमेगा माइनस chi, and this we represent as this quantity. So for any uh, phi or the incoming packet, and for any chi, that is for outgoing wave packet, where phi plus represents the actual state of the system at time t is equals to 0. Why actual state at time t is equals to 0? Because this is in fact psi, and similarly this is equals to psi. Yeah. So in fact these two quantities are basically psi, and this is in fact the actual state. Yeah, so this is actual state. So if this is actual state, then phi plus and chi minus, they are basically the actual state at time t is equals to 0. So we can say where phi plus represent actual state state of the system at time t is equals to 0 for an asymptote, that is psi n is in fact phi, and the vector chi minus represent the actual state at t is equals to 0 for the out asymptote. Yeah, या यानी दूसरे लफ्जों में psi out is in fact this chi state. So this is basically the representation of these two in fact states. So you can think about that is the incoming or the in asymptote, which is coming from t tending towards minus infinity to t is equals to 0. Then it basically converts into or evolve into an actual state psi at time t is equals to 0. And similarly, an outgoing particle would tend to out asymptote, that is, it evolves from from the actual state into an out state at time t is equals to 0. So these are the two, in fact, sort of states. Now next जो है हम मोलर ऑपरेटर और स्कैटरिंग ऑपरेटर ड्राइव करेंगे. Or then this would end sort of almost the scattering theory, and from the next day we will start the new topic. Yeah. Okay.